Suppose if you ask what is meant by current, I is what, sir? Then basically, in your 10th class, just I am trying to revise that part. Whatever, if it is a conductor, in the conductor there will be surplus of free electrons. Conductor itself, its meaning is having many number of free electrons. Those free electrons inside, okay, actually move very randomly, Nana. Okay, means like in random motion, like in the gas, in gases, how the molecules and atoms move. Okay, random motion. Due to that random motion, net movement for the you will get it zero now. That's why what he says here, if you want to move this electron from one end to the other end, what to do first? Okay, for that means in one particular direction, not like in zigzag random motion. Then he says it is a charge. Electron is nothing but charge, having the charge of 1 into charge on electron is 1.6 into 10 to the power of minus 19. Okay, that charge, if you want to move from one point to another point, in the previous chapter, what potential and capacitance, there what we understood, suppose if you maintain between 2 points not the same potential, some potential difference, like here 5 volts, there say some 7 volts. Okay, some potential difference between the two. Means directly I can say potential difference is 2 volts. Delta V is equals to 2 volts. Okay. Due to that potential difference, means trying to reconnect the part what we discussed previously. Generally, the positive charges tries to move from higher potential to lower potential, whereas negative charges tries to move from lower potential to higher potential. Okay. This point already we discussed in that chapter, Nana, potential and capacitance. So here, since the electron is a negative charge, it tries to move from lower potential to higher potential. That's why here it tries to move from lower 5 volts to higher 7 volts. Tries to move in this direction. Okay. Tries to move in that direction means it is not getting the random motion. It tries to move from particularly from one side to the other side, like in this direction. Okay. While flowing, not one electron, a surplus of electrons are there. So many electrons try to move in this direction, like million march. Okay, many electrons try to move. While moving, what he is saying, at one particular cross section, okay, how much charge crosses per second? Okay, suppose here n number of electrons cross this particular cross section in a given time. Okay, so I say immediately the total charge crossed there is equals to Ne. Okay, I already told in charges and fields chapter. That is the total charge crossed a particular cross section in a time. Okay. So what he is saying, in 1 second, how much charge crossed? Okay. As usual, the cross multiplication model. In t seconds, q amount of charge crossed this particular cross section. In 1 second, how much charge crossed? Okay. It is nothing but 1 into q by t, that is q by t is, we define it as electric current. Okay. So electric current, fundamentally we are getting one formula what you already know in your 10th class, I is equals to q by t. One fundamental, just recollect it. What almost 1 year back we means you learned in your schools. Okay. That is electric current is nothing but charge crossing one particular cross section, okay, in 1 second, right? And while crossing here, first of all, what the basic condition we applied here to flow the charge from one point to another point, fundamentally we have to maintain some potential difference. That potential difference here I set PD, the potential difference, taking it as P. Okay. Due to this potential difference, how much current flows through it? I is equals to Q by T. Right? And number 3 here, while flowing, major problem is this is a conductor and it is not the empty space. Inside the conductor means it is a solid now. Okay. Inside a solid, there are many number of atoms and you have surplus of free electrons, means these atoms already lost many number of electrons. These atoms lost electrons means each atom behaves as one positive ion like. So here those positive ions, when one electron tries to move from here to there, okay, through few ions tries to attract the electrons, few other ions try to decelerate the electron. Okay, means suppose one electron tries to move from here to there, the problem is this is also positive ion and crossing one is electron, negative and positive, some attraction will be there. So few ions try to decelerate, few other ions tries to accelerate. Okay. Decelerating means for the motion of the electron, the conductor itself, when you maintain some potential difference here, like V1 and V2, it is suppose some low potential and that is some high potential. Then immediately electrons while moving from low potential to high potential, here experiencing some opposition from the ions for their flow. The total opposition offered by the conductor is defined as resistance. This is the story. Okay. So here, what is meant by current? I explained here. The charge per unit time means charge per second. How much charge flows through a conductor in 1 second at a given cross section is the current. For the flow of current, here what is the basic condition? You have to maintain some potential difference. After maintaining, while the charge is flowing, what kind of opposition you get there, that opposition offered by the conductor is called as resistance. Simply. Okay. So the basic things here, whatever we require, I explained here now. I, V and R. So from this basic concept, what he says here, current to flow from one side to the other side, basically what we require, I already told here, potential difference. Okay, that formula already you know in your 10th class, okay, stated by Ohm, scientist Ohm. What he said, to flow the current, we have to maintain the potential difference. If this potential difference is more, the flow of current is also more. That is called as Ohm's law. What he stated it as, V is directly proportional to I. If the potential difference is more, the current flow is also more. Okay. And from this, in 10th class only, you know this formula actually, that Ohm's law V is equals to, I write here, I into the proportional constant is what we discussed, the resistance. It is called as Ohm's law. Okay, but one point I don't know whether you know it in 10th class or not. This Ohm's law, while stating, actually, we have to give one tagline, Anna. That
constant temperature, sir.
Yes. The tagline is at a constant temperature. We have to add this tagline. Okay. Problem is if you change the temperature while changing the potential difference, the resistance changes. That is the problem. Whereas Ohm stated R is the proportionality constant. Proportionality constant, that should be a constant in the equation. So to keep it as a constant, we have to maintain temperature constant. Okay. How it depends upon temperature, later we will discuss now. Right? And here, one by one, if we come to the applications of this part, right? If we come, that is, here, suppose I say, through a conductor, by maintaining some potential difference, suppose a cross section, selected some cross section. Okay. The charge crossing the cross section, all the times, it is equals to say some 5 coulombs. Okay. Then if I ask, what is the current flowing through the conductor? What do you say? From your side now.
Sir, Q by time taken to flow, sir.
That is the wrong what generally we do. Nana. Here, current is time dependent charge. Nana. I is equals to, we are saying it as Q by T means differential form, we have to write it as dQ by dt. Means the current is time dependent, okay, and the charge should also be time dependent. So here problem is, through a particular cross section, the charge crossing is constant, Q is equals to constant, okay, all the times 5 coulomb only, in 1 second or 2 seconds or 3 seconds or 4 seconds, whatever it may be. According to mathematics, you know, if Q is constant, directly you can say I is equals to how much you know it. Okay, differentiation of constant is 0. This is the problem now. That's why here don't come to misconcept here. If charge is constant passing through a conductor, then how much current flows? Directly we have to say that is equals to 0. Okay, this thing actually you have to understand when one source is connected to a capacitor. I don't know whether you still remember or not. Suppose if I maintain by connecting it to a source of constant potential difference 5 volts, right? Then here, what we say, if I ask what is the charge on each plate, I think you remembered it. Okay, that is nothing but Q is equals to, according to the formula, C into V, you can say. That is Q is equals to 5C. Whatever the C value they give, that we substitute and try to find out the charge. Okay, but now I am asking, here the charge is constant or variable? Is that charge constant or variable?
Constant.
Constant.
Yeah, good. Since it is constant, later if I connect this model to the current electricity here, what is the current flowing through the circuit if I ask?
0.
Obviously it is a 0. Very good. Okay. So here, when some DC source, which maintains constant potential, one DC source is connected to the capacitor, there we say the current flowing through the circuit is 0. Charge it will get, but problem is it is constant. If it is constant, just now we came to know, if it is constant, current flowing is equals to 0. Okay, very good. So here, there of course in capacitors, while interlinking these two concepts, what I say, when a capacitor is connected to the DC source, and that too that potential difference is constant, that's why Q is constant. If the potential difference is constant, not variable, okay, then current through it is equals to 0. That implies the capacitor does not allow the flow of the whatever the source connected here, DC source, flow of DC current, that is DC, direct current. This is one point, none for us actually objective. So here we understood when charge through particular cross section is constant, then obviously current through the conductor in the circuit is zero. And number two, here suppose if I want the current is constant, not Q constant. Okay, then from this previous knowledge, I think you understood what if Q is equals to constant, then I got I equals to 0. So Q should not be constant. Then how should it vary in the circuit, Nana? Current should be constant. Then Q I have to assume like, I think you did not follow my question. Suppose Q is equals to, if I take it as A T squared, one model. Q is
Sir, it needs to be single linear variable. Linear.
Means Q should be second order equation or first order?
First order, sir.
First order.
First order, sir.
Yeah, it should be first order.
First order.
Right. Means you may take it as like some constant into time or constant into time plus some other terms, whatever it may be. Okay. I think in both the cases, you will get from the first equation I can write I is equals to dq by dt. That is nothing but I write it as A. A is already constant, therefore I is constant. Or here even with this other constant also. Here also I say dq by dt, which is I write it as A1. Okay, I think you know the differentiation. Here also I am getting constant. That's why second point, what we understood from this concept, Nana, the charge should vary with the time, okay, linearly, or like one equation, mx plus c model, or y is equals to mx model. Okay, means what I am saying, the charge changes with the time as linearly like this, which is q is equals to at, or like this, q is equals to at plus b, or even like this also, q is equals to here minus at plus b. Okay, like y is equals to minus mx plus c. In the three cases, you will get some current, Nana, which is constant. Okay, here I is equals to u, there also I equals to u, here also I is equals to minus u. Minus a means opposite direction. Current is flowing in opposite direction. Why? Because charge is decreasing. So here keep in mind, Nana, the student may get some confusion. What till now, what you discussed in the previous classes, the charges and fields chapter, or the potential and capacitance chapter, there you give some amount of charge to one substance actually there. Okay, you are giving the charge to one substance and that charge resides on the surface. Means actually they are charged either conductors or insulators. You are giving the charge now. Means forcibly you removed some number of electrons from the substance, or you added some number of electrons to the substance from some external source. Okay, or some by external method like friction or contact or some other method. Okay, here don't get confused, Nana. Whereas in this chapter, what I took, this is a conductor I told. So student may feel that all the charge resides over the surface. Okay. Here first question is where I give the charge to the substance. Actually, that is not charged conductor. It is a neutral conductor, Nana. Actually, I did not give any charge or I did not remove any number of electrons from the conductor. Okay. So here electrons came out of atoms, but they are not coming out of the substance. Okay, means atoms lost electrons, but not the substance. So here, whatever the electrons lost by the atoms, they are still in the house only. Okay, they are not keeping their leg out. Okay, in the corona time. So still they are living inside. Still they are living inside means inside the number of family members not changing none. That's why here neither loss nor gain. Okay, and we are not inviting any our of relatives also. Okay, neither inviting nor going out. So it is not a charged conductor, but inside existing. Okay, number of surplus of free electrons are there. Why? Because most of the atoms lost the electrons inside and left free electrons there, and they are not coming out of the substance. Okay, that's why in this case it is actually the neutral conductor what I put now. It is a conductor, but it is neutral conductor. In that neutral conductor, here those electrons are unnecessarily randomly moving inside. To streamline them to flow in one particular direction, I maintain some potential difference here. Okay. So suppose if I maintain some potential difference, suppose if I keep Narasimha Rao sir here and Sharat sir there, then obviously we go out of Narasimha Rao sir and approach the Sharat sir. Some potential difference there. Okay. So here they move from one side to the other side, but no electron is not is coming out of the substance now. That's why while flowing, keep in mind it is not a charged conductor. It is always neutral conductor. The existing electrons try to move from one side to the other side. While flowing, if the charge crossing a particular cross section changes with the time, then you will get some current through the conductor. This is the story what we discussed. If I changes with the time, not constant, that what will be the charge in a given time. Here what he says, practically when the electrons are flowing from here to there, from one side to other side, by maintaining some potential difference here. Okay. And that current is suppose constant, I, that is constant. Okay. And here current is nothing but I already told Q by T, Q is NE by T. Okay. This we use when I is equals to constant, right? NE by T. And here number of electrons passing through one particular cross section divided by time. Okay. And here when that current is flowing through a conductor, electrons here keep in mind Nana, flow of electrons and flow of current long back they assume in opposite direction. Just with one small misconcept, that time in 16th century this part of this concept was explained. By that time they don't know about electrons. Okay, this is a modern concept. In 19th and 20th century they found the electron. So that time they assumed current flow means nothing but some positive charge is flowing from one side to other side. This one what they explain, I is equals to actually they explain some plus Q by T. They don't know about NE by T. Okay. So by that misconcept, what happened after coming to 19th and 20th century, they found practically the current is actually flow of nothing but electrons, but electrons are flowing, generally flow from low potential to high potential. Okay. Why? Because they have negative charge, but they assumed the current flows from high potential to low potential. That's why what they gave finally, instead of changing all the books, they came to give one bottom line here. What is that? Assume the flow of current in opposite direction to the flow of current. So just they change it with one bottom line, Nana, without changing everything from the books. Okay, they change it like just assume the flow of current and flow of electrons in opposite directions. That's why nothing we are changing here. Just we are assuming their directions are in opposite direction. So here, suppose if I assume the current in this direction, electrons are flowing in opposite direction. While flowing, somewhere here I explained the concept, Nana. You will get some acceleration and deceleration simultaneously. That acceleration, due to that acceleration, they try to accelerate, but think wisely like some intelligent student. While flowing this electron from one end to the other end, okay, due to the potential difference, actually some electric field will be generated between the ends of conductors. That already you know in the chapter of potentials, I think still you remember, minus dou V by dou X. And that potential difference is constant. We write it as V by D, potential difference divided by D. So some electric field is maintained there. Due to that electric field, here suppose electric field is formed in this direction due to the potential difference. Then immediately the negative charges are accelerated in opposite direction since electron is a negative charge. This is modern theory now, what I'm explaining. Okay, electron tries to accelerate in opposite direction and experiences some force. That force is equals to E into Q on each electron, you know, in again charges and fields chapter. By that it experiencing some acceleration, A is equals to E, Q is charge on electron E by M. This is the acceleration there experienced by an electron. Okay, but due to the pull of all ions, it can't move in a straight line now. Okay, where it gets the net force in that direction, it tries to bend. That's why even though they are very close to each other in solids particularly, they try to bend from their path and there is a chance to make the collisions with the other ions. Okay, while colliding, if you think more deep into the concept, those electrons may be again captured by the ions. Okay, why? Because it is positive. No, positive means lack of electron. So there is a chance to capture, or suppose it is hitting at the edges of the atom, there is a chance to deviate its path like this. Again may hit the other ion here. Again there is second possibility, capture by the ion, or else again maybe reflect, means after collision changes its direction like this. And if you observe there, okay, the electron is not going like here on the road as CM or PM or president. Okay. While flowing, it is facing many number of collisions, just like in Sultan Bazar. Of course, not nowadays. Okay, not in this Corona time. Right? There is a problem, Nana. So these electrons here experiencing many number of collisions. Okay. And that too, this is the story about one electron, Nana. Likewise, many number of electrons are here crossing one end to the other end. While crossing, they are colliding the atoms continuously. Okay, means ions. Collision means there is a chance of some loss of energy. That's why here, if you see practically, when the current is passing through a conductor, after certain time, if you touch the, here, not straight away the conductor, no, you may feel the shock. Even the surface, that sheath, plastic sheath, okay, some insulation layer they gave. Even if you touch that insulation layer, you may feel some hotness of the on the wire. Okay. How you get that hotness? Here at each collision, it is losing some amount of energy. In physics, loss of energy is not there. That should be converted into some other form. Okay, that energy is transformed into heat. Okay, leave it. That is one part. And here my intention is, here in certain given time, not one electron, many number of electrons are making the collisions. Okay, while colliding, we say, suppose there are n number of electrons are colliding. N number of electrons are making the collisions. Okay, here in this case. And in those n number of electrons, while making the collisions, means just one collision, I am saying about one collision. Okay, means in this time, number of electrons are making the collisions. And here, suppose in those number of electrons, some ith particle, means ith electron, some one electron, okay, like a third electron or fourth electron, one electron. Okay. While here, before making the collision from one to the other, here it will be accelerated by this acceleration E by m. So here, if you ask after a time t, before making the second collision between these two, means already one collision is over. Second collision, first and second collision. In a time t, what will be the final velocity of ith particle, if you ask? Then I have to use the formula v is equals to u plus at. Why? Because acceleration is constant, no variable is there. So E by m into t, where u is the initial velocity of that ith particle. Okay. Likewise, there are n number of electrons in the same time. Okay. So for all particles, if you take the average of, means V1, which is I write is a U1 plus E by m into t. Second particle V2 is equals to U2 plus E by m into t in the same time. Third particle, fourth particle, so on, nth particle Un plus E by m into t. Okay, then the average of those final velocities of n particles is V average, called as drift velocity. This is called as drift velocity. Okay, and their initial directions average, if you take for all particles, the average velocity you will get it as 0. Why? Because while making the collision, first particle may move in this direction. After the first collision, second particle may move in that direction. Third particle may move in this direction. Fourth particle may move. Fifth particle may move. Means if you take the average of all, you will get the average velocity is equals to 0. And sometimes while making the collisions, few particles will move like this also. That's what I told. Average will be 0 for n number of particles. So here, the final velocity, what it is getting, means all the n particles average, okay, is the drift velocity. It is the average velocity equals to 0 plus E by m into that time average here we have. Okay, that average time here is called as relaxation time, represented with the tau. Okay, so basically, if you ask what is that average velocity in a given relaxation time t star, that average velocity, fundamentally I say called as drift velocity, is equals to E by m into the relaxation time tau. Okay, how this drift velocity you interrelate with current, tomorrow we will discuss now. Okay.